Welcome back, everyone, to The Deep Dive. We love to go deep, and today's no different. We're going to dive into something you already kind of know, forces and friction. But we're going to uncover some fascinating stuff you probably never thought about before.
It's funny how forces and friction are so fundamental. Like, we all learn about them in school, but there's still so much more to discover about them.
Absolutely. Like, we all know forces are behind every push and pull.
Right.
But think about it this way. What about those forces that are, like, running the entire universe?
Yeah.
The big picture stuff.
Yeah, that's where we get into those fundamental forces of nature, right? The ones that govern everything. So, like, we've got gravity. Obviously, everyone knows about gravity. It's what's keeping us on this planet.
Keeps our feet on the ground.
Yeah.
But it's not just about us. It's about the whole universe.
Right. It's holding the moon in orbit. It's what created the stars and galaxies. It's pretty powerful stuff.
Super powerful. And then there's another big one, the electromagnetic force, right? So what's that all about?
Well, the electromagnetic force, that's responsible for electricity. It's responsible for magnetism, light. It's the reason we can see and why our electronics work, even, like the warmth of the sun.
So anytime we flip a light switch, we're messing with the electromagnetic force. That's kind of cool.
Exactly. Yeah. And then things get even more wild when we start thinking about the strong and weak nuclear forces. Those operate at the tiniest level, like inside the nucleus of an atom.
So these are forces we don't really experience directly in our lives.
Not directly, no, but they're essential for matter itself to exist. Like, without them, atoms would just fall apart. No us, no universe, nothing.
They're like the glue holding everything together.
Exactly. The universe is super glue. But okay, let's, zoom out a little bit from those universe-level forces and talk about the forces we actually see every day, right? Like, the forces affecting all the objects around us. And we can break those down into three main types, I guess. So we've got, field forces, contact forces, and attachment forces.
Okay, so field forces, those are the ones that act over a distance. So like gravity is a field force, right? Like we don't actually have to touch the earth to feel its pull.
Exactly, yeah. And think about static cling. Like, when your clothes stick together, that's the electromagnetic force acting even without direct contact.
Yeah, so with contact forces, it's got to be like touchy-feely.
Yeah, it's all about that direct contact. So, like, pushing a shopping cart or when friction slows down your bike.
Okay, I get it. And then those attachment forces, those are the forces that happen when something's like connected to something else.
Yeah, like think about a rope pulling a swing. The tension in that rope, that's an attachment force.
Or like the spring force in a trampoline. Right, you jump and that spring pushes back against you.
Exactly. It's like the object is trying to resist changing its shape, and that resistance, that's where the force comes from.
Cool. Okay, so we've got these sources all around us acting in different ways. But how do we actually know how they affect motion? Like, is there some kind of, like, rule book for how stuff moves?
Well, there is. It's called Newton's laws of motion. And yeah, they're kind of like the rule book for understanding how things move. They explain why things move the way they do.
Okay, so Newton's first law, that's the one about inertia, right?
Yeah.
It basically says, like, things like to keep doing what they're already doing.
Yeah, an object at rest stays at rest. An object in motion stays in motion, unless some outside force acts on it.
Okay, so like a soccer ball on the field. It's just going to sit there until someone kicks it.
Exactly. Or when you're in a car and you slam on the brakes and you feel yourself, like, jolting forward, that's inertia too. Your body wants to keep moving at the same speed.
Oh, yeah. I hate that feeling.
And it's not just about speed, it's also about direction. Think about mud flying off a spinning tire. That's inertia of direction. That mud wants to keep going straight even though the tire's turning.
Makes sense. All right, so what about Newton's second law? What's that one all about?
So the second law gets a little bit more mathematical. It gives us an equation. FMA, force equals mass times acceleration. Basically, it means the more force you apply to something, the faster it'll speed up.
So if I push a shopping cart really hard, it's going to accelerate faster than if I just give it a little nudge.
Exactly. And the heavier the object, the more force you need to get it moving at the same speed. Think about pushing a shopping cart again. A full cart is harder to push than an empty one, right?
Cool.
Because it has more mass.
Way hard. Okay, so that makes sense. More force, more acceleration, and heavier objects need more force to move.
Now, Newton's third law, this is where things get a little bit mind-bending. It says, for every action, there is an equal and opposite reaction, meaning forces always come in pairs.
This one's always a bit tricky. But okay, so like when I jump up, I'm pushing down on the ground, and the ground is pushing back up on me with the same amount of force, right?
Exactly. That's what propels you upwards. Think about a swimmer. they push water backwards to move themselves forward. Or rocket launching, the exhaust goes down, the rocket goes up.
Okay, I think I'm starting to see it. But if the forces are equal and opposite, how come they don't just cancel each other out?
Well, that's the key. The forces are acting on different objects, so they don't cancel out, they create motion.
That makes a lot more sense now. Okay, so we've got all these forces, and Newton's laws tell us how they work. But how do we actually visualize all of this? Like, when we're trying to understand how forces are acting on an object, is there a way to, like, draw it out?
There is. We use something called a free body diagram. It's a way to simplify and visualize all the forces acting on a particular object at one time.
It's kind of like a snapshot.
Exactly. So imagine a book just sitting on a table. In a free body diagram, we'd show the force of gravity pulling the book down and the normal force from the table pushing it up.
Okay, and those forces are balanced, which is why the book isn't moving, right?
Right. And if someone came along and pushed the book sideways, we could add that force to the diagram and see how the whole balance changes and how it would make the book move.
So a free body diagram lets us see why things move
Yeah.
or don't move. It's like a tool for figuring out the forces at play.
Exactly. And it's a really useful tool for physicists and engineers. It helps us make sense of complex situations.
Awesome. Okay, so we've covered a lot about forces, but let's talk about something we all experience every day and probably don't appreciate enough: friction.
Yeah.
A lot of times we think of it as a bad thing, right? Something that slows things down or makes them harder to move.
Well, yeah, sometimes friction can be a pain. But think about it. Could you even walk without friction?
Good point. It's actually super important for a lot of things we do.
Absolutely. It's what allows us to walk, write, drive a car. It's the reason your furniture doesn't just slide around your house.
So maybe it's more like a necessary evil. It has its downsides, but it's also essential.
Yeah, I think that's a good way to put it. And to understand it better, it's helpful to know there are two main types of friction: static friction and dynamic friction.
Okay, so static friction is what keeps things from moving in the first place. Like when you're standing still, it's the grip between your shoes and the floor.
Exactly. And dynamic friction, sometimes called kinetic friction, is the friction that happens when things are already moving. So that's the friction that, like, slows down a rolling ball or a sliding box.
Okay, so static friction is when things are at rest, and dynamic friction is when they're in motion.
Exactly. And we can even measure how sticky two surfaces are with this thing called the friction coefficient.
The higher the coefficient, the more friction, right?
Yep. So steel on steel, for example, has a high coefficient of friction. That's why it's hard to slide steel across steel. But Teflon, the stuff they use in nonstick pans, that has a really low coefficient, making things slide super easily.
That makes sense. And is there like a maximum amount of static friction that you have to overcome to get something to move?
There is. It's called limiting friction. It's the most static friction you can have before an object starts moving.
So like if you're pushing a really heavy box, you need to overcome that limiting friction to even get it to budge.
Exactly. And once it starts moving, it usually becomes a bit easier to keep it going because you're dealing with dynamic friction then. But, it's still a constant battle against friction.
Like a constant tug of war between the force you're applying and the friction trying to stop you. It's amazing how something that seems so simple can actually be pretty complex.
Yeah, it really is. And it affects so many things in our world.
Totally. Well, I think we've covered a lot of ground here today, from the fundamental forces of the universe to the nitty-gritty of friction.
It's been quite a journey.
And we're not done yet. We've got so much more to unpack about friction and its role in our lives.
Yeah, and we'll get into that.
Stay tuned. We'll be right back.
Right after this. Before we were talking about how friction's kind of like always there, always working against us. But what if we could reduce it, make things move more smoothly?
Yeah, that makes sense. Especially like when you think about, how much fuel cars waste because of friction.
Yeah.
Or like how machines wear out faster.
Exactly. So we've come up with some pretty clever ways to minimize friction. Like one way is polishing. If you make a surface really smooth, you actually reduce the friction.
Oh, yeah. It's like when you sand wood. The smoother it gets, the less friction there is.
Exactly. And then there's lubrication. That's where you put something slippery between two surfaces to reduce the friction.
Like oil in an engine.
Exactly. Or grease on a bike chain. That keeps things moving smoothly and prevents wear and tear.
Oh, yeah. So lubrication is like adding a layer of slipperiness.
Exactly. And then you've got streamlining. That's like designing things with shapes that reduce air resistance.
So like sports cars. They're all sleek and curvy.
Yeah. Or airplanes. They're designed to cut through the air with as little resistance as possible.
So it's all about reducing friction, To improve speed and efficiency.
Right. Whether it's, polishing something tiny or designing a whole airplane, we're constantly trying to outsmart friction.
Makes sense. But friction's not just about solid objects, right?
You're right. We also have to think about friction in fluids.
Fluids.
Yeah, liquids and gases.
Oh, right.
And that type of friction is called viscosity.
Viscosity. Okay, so like honey has high viscosity. It's really thick and slow to pour.
Right. And water has lower viscosity. It flows easily.
Okay. And air has viscosity too, right?
It does. That's what creates air resistance, like when you're riding a bike into the wind.
Yeah. I hate that.
So viscosity affects all kinds of things, from how fast a raindrop falls to how airplanes are designed. Pretty amazing, right?
Totally. Friction is way more important and way more complicated than I thought.
It really is. But hey, let's switch gears for a sec and talk about another cool type of force. Spring force.
Okay. Springs, those are fun. So what makes them so special?
Well, springs can exert a force when they're stretched or compressed. They kind of push back when you deform them.
Yeah, like if you push down on a spring, it pushes right back up at you.
Exactly. And that's what we call the spring force.
Okay, so what's the science behind that?
Well, there's this law called Hooke's law, and it describes how springs behave. It basically says the more you stretch or compress a spring, the more force it'll exert to try and go back to its original shape.
So the spring is always trying to, fight back against the change.
Yeah, that's a good way to think about it. And we can measure how stiff a spring is using something called the spring constant.
Spring constant, what's that?
It's basically a number that tells you how much force you need to stretch or compress the spring a certain amount.
So a really stiff spring, like in a car suspension, would have a higher spring constant than, say, a spring in a pen.
Exactly. Car springs need to be super strong to support the weight of the car. Pen springs, not so much.
Okay, so Hooke's law tells us how springs work, and the spring constant tells us how strong they are.
Exactly. And, all these ideas, forces, friction, springs, they're not just abstract ideas. They have real implications for how we design and build things.
Right. I mean, think about building a robot that could move like a human. That's a huge engineering challenge.
Huge. We take our own movements for granted, but getting a robot to do those same things is incredibly complex.
So what are some of the challenges?
Well, first, you've got to think about all the forces involved. Like when a robot walks, it has to push against the ground with just the right amount of force to move forward, but also stay balanced.
So it doesn't fall over.
Exactly. And friction is crucial there, too. The robot's feet have to grip the ground enough to push off, but not so much that they get stuck.
Oh, yeah. It'd be like trying to walk on ice. No friction, no control.
Exactly. And then think about more complex movements like picking up an object. The robot has to apply the right amount of force to grip it, but not crush it.
It's like a delicate dance. Too much force, and you break something. Too little, and you drop it.
Totally. And that's just the beginning. If you want the robot to run, jump, dance, the calculations get even more complex.
So how do engineers actually tackle these challenges?
Well, one of the biggest things is sensing. Robots need to be able to sense their environment like we do with our eyes, ears, and sense of touch.
So they need sensors.
Yeah, things like cameras, pressure sensors, even tactile sensors that can mimic the sense of touch.
Wow. But it's not just about having the sensors. They have to be able to process that information to make decisions.
Exactly. It takes sophisticated algorithms and machine learning so the robot can learn from its experiences and get better over time.
Okay. That's pretty amazing. But what about power? I mean, robots need a lot of energy to move around, right? A lot more than humans.
Yeah, that's another challenge. Engineers are always working on making robots more energy efficient.
So using lighter materials, better batteries.
Exactly. So it's a really interdisciplinary field. You've got robotics, but you've also got material science, computer science, even neuroscience.
Wow. So it's not just about building cool robots. This research could have a lot of practical applications.
Oh, definitely. Think about prosthetics. If we can understand how humans move, we can build better prosthetic limbs that are more intuitive and responsive.
That would be amazing.
And think about manufacturing. Robots are already used in factories, but imagine them being able to do even more complex tasks. It would make things more efficient and safer.
Yeah, I can even imagine robots being used in search and rescue, like going into dangerous environments after a disaster.
Absolutely. So the possibilities are really exciting. And it all comes back to understanding those fundamental forces we were talking about earlier.
Yeah, from those tiny forces inside atoms to the huge forces shaping galaxies, they're all connected.
It's pretty mind-blowing. But, Sometimes we get so caught up in the big picture, we forget to appreciate the smaller ways these forces shape our everyday lives.
That's true. We take so much for granted, like even something as simple as how different surfaces feel when we touch them.
Right. Some things feel smooth, some feel rough. That's all about friction.
Oh yeah. So when we say something feels smooth, we're really saying it has low friction against our skin.
Exactly. And smooth surfaces are easier to clean because dirt has less to grip onto.
That's a good point. I never thought about it like that. And what about like how we hold things?
Well, think about your fingerprints. Those widges actually increase the friction, which is why it's easier to hold things.
Oh, that's why it's so hard to hold on to something when your hands are wet.
Exactly. The water reduces the friction, making things slippery.
Makes sense. And friction's not just about grip, right?
Nope. It's also involved in our sense of touch.
So, like when we rub our fingers over something, the friction creates tiny vibrations that our skin can feel.
Right. That's how we perceive texture and even temperature.
Wow. So without friction, our sense of touch would be pretty limited.
Yeah, we wouldn't be able to experience the world in the same way.
It's like friction is this hidden language, always communicating with us.
It really is. And think about something as simple as writing with a pen. Friction is essential for that too.
Oh yeah, without friction, the pen would just slide across the paper.
Exactly. And different types of pens create different lines because of how the ink interacts with the paper.
So a ballpoint pen uses thicker ink, needs more friction, creates a bolder line.
Right. And a fountain pen, with its thinner ink, needs less friction, so the lines are finer.
Oh, and the paper matters too, right?
Absolutely. A rougher paper creates more friction, so the lines look different than on a smooth paper. It's all connected.
It's amazing how friction can be so subtle. And it's not just about writing. Think about cooking.
Oh, yeah. Like using a nonstick pan versus a cast iron skillet. That's all about friction.
Right, nonstick is all about minimizing friction.
Yeah.
Cast iron, you want that friction to get those crispy textures.
Exactly. And it's the same with baking. The friction between the dough and the pan helps create the crust on bread.
Wow. So friction can be a good thing or a bad thing, depending on what you're trying to achieve.
Absolutely. It's all about understanding how to use it to your advantage.
This whole conversation has really made me appreciate friction in a whole new way.
Yeah.
It's involved in so much more than I realized.
It really is. It's like this unsung hero silently working behind the scenes, making our lives possible.
Totally. From holding a cup to
Mhm.
writing a letter to cooking a meal, it's everywhere. So we've been talking about how friction is like this everyday thing, right?
Right.
But it's also a big deal in like science and engineering and stuff too, right?
Oh, absolutely. Like engineers, they got to think about forces and friction all the time, when they're designing things like bridges and buildings and cars.
Oh yeah, they have to make sure those things can handle all the forces they're going to experience.
Exactly. Like think about a bridge. It's got to deal with gravity pulling it down, the weight of all the cars driving on it, even wind pushing against it.
Wow, that's a lot. So how do they make sure the bridge doesn't just like collapse?
Well, they use their knowledge of forces to calculate exactly how strong the bridge needs to be. They have to choose the right materials, the right shapes. Everything's going to be designed just right to distribute those forces so nothing breaks.
And friction is important too, right?
Totally. Especially in the joints and connections of the bridge. You need enough friction to keep things from slipping and sliding around.
Okay, so friction is like the glue that holds it all together.
In a way, yeah. And it's not just about bridges. Think about all the new materials scientists are creating all the time.
Oh yeah, like super strong materials or super lightweight ones.
Right. And sometimes they need materials with very specific frictional properties, like maybe they need something super slippery.
Oh, like for those non-stick pans.
Exactly. Or they might need a material with a lot of friction, like for tires on a car.
Right, so the tires can grip the road. It's amazing how we can manipulate friction to create materials that do all sorts of things.
It really is. And it's not just in engineering and material science. Friction's a big deal in medicine too.
Oh, really? Like how?
Well, think about things like implants, artificial hips or knees.
Right, they're putting those inside people's bodies.
Exactly. So those implants, they got to be designed to work smoothly with the human body, right?
Yeah.
The engineers have to consider how much friction there's going to be between the implant and the surrounding tissue.
Oh, I see. So they have to find materials that won't cause too much friction so the implant doesn't wear out or irritate the body.
Exactly. They need to make sure it's biocompatible so it can function properly for years and years. It's pretty incredible, right?
Totally. It's amazing how these ideas we've been talking about forces and friction, they show up everywhere, from everyday stuff to super high-tech stuff.
And it all goes back to those fundamental forces we talked about at the beginning,
Hmm.
the forces that govern the entire universe.
Right, from the smallest atoms to the largest galaxies.
Exactly. It's all connected.
It's a pretty awesome reminder that science isn't just about, like, equations and formulas. It's about understanding the forces that shape our world and using that knowledge to make things better.
And to solve problems.
Yeah.
And to create new things.
Exactly. Well, this deep dive has been amazing. I feel like I've learned so much about forces and friction.
Me too. And I hope our listeners feel the same way.
I'm sure they do.
Mm.
It's just been so fascinating to see how these things are at work all around us all the time.
Right. And hopefully now, people will start to notice them a little bit more, like the next time you pick up a pen or walk down the street or cook dinner, you might just think about the forces and friction that are making it all possible.
I know I will. It's like a whole new way of looking at the world.
Yeah.
Well, that's about all the time we have for today.
Thanks for joining us.
Thanks for listening, everyone.